Welcome to another tutorial of Proflan YouTube channel. In this particular video, we're going to have a discussion of past paper exam questions on the topic space physics. This is a topic in Cambridge Igcse physics and is one of a new topic in the specification that was introduced around 2022. That was then it was tested first 2023. So we are going to have a detailed discussion so that you can be able to have a deep understanding on how to answer questions regarding this topic. If you are new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload another tutorial, you'll be notified. Now, moving to the question, we can see here we have a figure that represents different positions of the moon as it rotates around the earth. Remember, a moon does not produce its own light because it's a satellite, and it just reflects the light that comes from the sun. Now you can see here we are asked to state the position of the moon where the observer on the earth sees there is a quarter moon. And the way to respond to that is either position A or E, where the observer sees the full moon is position G. Now, let me take this chance so that I can be able to put on different shapes of the moon that I'm gonna experience. Maybe in the coming exam, May, June exams, you may not be asked this question. Another question may be asked here. So, orbit of the moon around the earth, and you need to remember that the orbit of the moon is usually circular and it's around the earth. So as the sun, as the moon moves around the earth, we are going to identify that each part will be facing the sun. A half of the part will be facing the sun. It will be dark. This section here will be dark because it's facing away from the sun, because our sun is on this region here. Yeah, so this part will be dark, the part that is facing away from the bright side of the moon. So here is where we have the new moon, and the new moon basically it's not usually visible. You cannot be able to see the new moon. We have this part here. We have a waning crescent at this point. Waning. This is a waning crescent. At this point, we have a waxing crescent. At this point, that's something I need you to remember. As the moon is moving in this stage like this, it's getting dark, it's getting dimmer and dimmer as it's moving this way. Now past the new moon, it will start becoming brighter. So that's why we are calling it a waxing crescent. It's becoming, now this crescent is becoming brighter, but this is a waning crescent which is becoming dimmer to become a new moon. Then at this lower point here, we have the third quarter. We can call it a third quarter. And at the top here, we have the first quarter. First quarter. Moving on this other side here, we have now, because the moon is getting brighter and brighter in this direction, so we can call it a waxing gibbous. We have a waxing gibbous. And the shape for that, the shape for the waxing gibbous is just like that, waxing gibbous. And at this point here, we are going to have a full moon. Down here, as the moon is moving from a full moon down, it's becoming now dimmer. And then we have what we call a waning gibbous. A waning gibbous. Waning gibbous. Yeah, those are different positions, the different shapes of the moon as it rotates around the earth. We are supposed to state here also the approximate time for the moon to orbit the earth. That is approximately 27 to 30 days. 27 to 30 days. So, but as a student, you are not going to write a range. You have to write exact number of days. So the moment you write this, either this and this, you are going to earn 1 mark at this point, and also you earn another mark at this point. 30 days also you're gonna earn 1 mark at that point. Now let's move to the next question. The next question that you really need to understand how to work out is the average orbital speed. If you are asked about average orbital speed, the formula that you should be using is the formula 2 pi r over t, where t is the periodic time. So if we are talking of the sun, and the sun, remember, is a star that generates its own heat and light through the fusion of the nuclear fusion or nuclear reactions that are taking place. Then we have a Earth here, a planet Earth, which is orbiting this star. So you need to realize that the speed at which the planet orbits the star is called the orbital speed. And the orbital speed is going to be equal to the distance around the total circumference of this orbit, which is given by 2 pi r. And actually this gives us the radius, the distance from the sun to the earth gives us the radius, and time, t, is the time it takes to go around the orbit. Now we are going to apply the formula, and you have to ensure that your time is in hours, because the sun takes the moon, the planet Earth takes 365 days to orbit around the sun. So we are going to multiply 365 times 24, because there are 24 hours in a day, so that we can be able to get our answer in kilometer. We are going to get our answer in kilometer, so that we can be able to get our answer given in kilometer per hour. We shall give our answer in kilometer per hour. Okay, so we are also told that the speed of light in a vacuum is 3.0 times 10 raised to power 8. We are supposed to calculate the time taken for light, calculate the time taken for the light from the sun to reach the earth. So what you need to know is that the distance from the sun to the earth is equivalent to 1.5 times 10 raised to power 8 kilometers. So that will mean we are going to use the formula time is distance over speed, because speed we know is distance over time. So if we rearrange this formula, we are going to get this formula that we have at this point. So applying this formula with the distance 1.5 times 10 raised to power 8, in order to get the time, in seconds, the time in seconds, I'm going to ensure that my speed also is in meter per second, because if you look at the question that we were having at the top here, it was 1.5 times 10 raised power 8 kilometers. So I have to ensure that this distance is in meters. So I will multiply this by 1,000, which is the same as 10 power 3. And that's why I did that at this point. Because speed of light in a vacuum is 3.0 times 10 raised power 8 meters per second. So this distance also must be in meters in order to get our time in 500 seconds. And you are going to transfer that answer here to make the examiner happy, and you shall get 2 marks for that case. Moving to question number 11, this was a question that was tested in the recent exams. And let's see, state the condition required for a protostar to become a stable star. So I need you to realize that formation of a star starts when the gas and dust particles called nebulae are drawn to close together by the gravitational force. So then the star, now when fusion of hydrogen and hydrogen leading to the formation of helium begin, the star now enter a stage that is known as a protostar. Now, when it's at a protostar, remember there is outward force that will be created due to the high temperature and pressure within the core of the star. Then when this outward force is balanced with the inward gravitational force that is pulling the dust particles together, then the star now becomes a stable star. So the condition for a protostar to become a stable star is one, that inward gravitational force that draws nebulae close together balances with the outward force due to the high temperature and pressure that's being created from the core of a star. Right, so when a star now is at the stable star, it will stay there for billion and billion of years. If it was a low mass star, once all the fusion of hydrogen is done, the star will move to a red giant. Then in the red giant, the star will continue fusion of helium and helium to lead formation of heavy metals. Then when all the helium is used up in the red giant stage, then the star will now go to another stage, which is called a white dwarf, which will finally cool down to become black dwarf. That is for a life cycle of a low mass star. Low mass stars, they follow the life cycle. Let me just write for you. It moved from protostar. It gets to stable main sequence stable star, main sequence stable star, which is called the main sequence. Then it becomes red giant. And in the stable star and protostar, fusion of hydrogen plus hydrogen takes place, leading to the formation of helium. And in the red giant, helium plus helium leading to heavy metals. When all the helium is used up, the star will become a white dwarf. And finally, it cools down to become a black dwarf. Yeah, which also at the white dwarf, some of the particles of some of the part of the star is shed off in form of interstellar nebulae, which will also lead to the formation of other stars. But when we come, we talk of the formation of or the life cycle of massive star or star which have larger masses than the sun. it will follow a different life cycle. It will start as a protostar, it becomes a main sequence stable star, then now it doesn't become a red giant, it becomes a red super giant, which explode as a supernova that then finally becomes a neutron star or a black hole. Now let's move down. You'll also need to know how to define Hubble's constant. Hubble constant, and the Hubble constant is actually a ratio of the speed at which a galaxy is moving away from the Earth to its distance from the Earth. Remember, Hubble's constant is used to, rather, Hubble's law is used to determine the speed at which a galaxy is moving away, or you can be able to use Hubble's law to determine the distance of a galaxy. So this is the formula for Hubble's law, and Hubble's constant is obtained from v, which is the speed of the galaxy, divided by the distance of the galaxy from Earth. So this formula for written here is not necessary for you to define that, but I've just written it so that you can be able to understand where I got this definition from. Now state the equation which gives the estimate age of the universe. The age of the universe is given by T is equals to 1 over Hubble's constant. Where do we get this formula from? Where do we get this formula from? We have already said that Hubble's law is given by this formula V over T. But remember, if a galaxy is moving at a speed v, then we can be able to say that v is equals to, if a galaxy is moving at this speed, yeah, let's talk of a galaxy, and this is the Earth, and a galaxy somewhere here is at the distance d from Earth. So if it has taken some time t to move, then its speed will be v is equal to d over t, right? Then which will mean that from this we can now say that all right, so using this formula we can be able to work out the age of the universe, and we're going to say 1 over Hubble's constant, and Hubble's constant is seated here. So we are going to say 1 over 2.2 times 10 raised to the power negative 18. If you work it out, you are going to get 4.5 times 10 raised to the power 17 seconds as the age of the universe. Let's go and see the next question. Also, that has ever been tested. We are told that the sun is one of many billion of stars in the Milky Way, and the sun emits a very large quantity of energy as electromagnetic radiation. State the 3 regions of the electromagnetic spectrum in which the sun emits the most energy. Ultraviolet, which usually affect our skin, are emitted by the sun. Also visible light, that's why you can be able to see objects around, is emitted from the sun. And also we feel some heat that is coming from the sun as in form of infrared. Electromagnetic radiation from the sun travels at the speed of 3.0 times 10 to the power 8, and the radiation takes 500 seconds to reach the Earth. Now, how do you calculate the distance? Distance is given by the formula speed times time. But if you look at this, you are given the speed and you have the time. Then if you want to work out the distance between the sun and the Earth, we are going to apply the formula, and that's going to give us 1.5 times 10 raised to the power 11 meters. Approximately 4.6 billion years ago, the sun formed from an interstellar cloud of the gas and became a stable star. Describe and explain what happens as the interstellar cloud of gas forms a protostar. These gas and dust particles, which are known as the nebulae, are drawn together by gravitational force. This results to high temperature and pressure and fusion of hydrogen and hydrogen begin. Remember, when gravity pulls these gas and dust particles together, hydrogen and hydrogen fusion will begin, because for you to fuse hydrogen you need high temperature and pressure. Now, since it's sufficient in this setup, then there is a nuclear reaction that is set up, which result to the release and formation of high formation of enormous amount of heat, that is energy that is released to the space. Yeah. So the source of energy from the sun is due to fusion of hydrogen and hydrogen, leading to the formation of helium. But in the process, because this is a nuclear reaction, a lot of energy is released, that even the one that we get to enjoy on Earth here. Describe and explain what happens as the protostar becomes stable. For a protostar to become stable, the outward force must balance with the inward gravitational force. Because remember, I mentioned and I opined in this video that gas and dust particles, which are called nebulae, are drawn together by gravitational force. Gravity pulls these gas and dust particles in space and roll them into maybe a ball. Then in the process, since these nebulae contain hydrogen nuclei, since there is high temperature and pressure due to the compressive force of the gravitational force, then fusion of hydrogen and hydrogen begin. But in the process, because this is a nuclear reaction, then there will be high temperature and pressure that will be now created outward. Now, when these two forces, outward forces, is balanced with the inward gravitational force, then the star enters into a stage which is called the main sequence, which is a stable star. Right. So another kind of question that you may be asked is to state how two other types of natural objects that orbit the sun. That is a comet, we have minor planets, we have dwarf planets, we have asteroids. Those are natural objects that orbit the Earth. And we need also to understand the shape of planets, that is of the orbit of planets, that is actually elliptical, meaning that if the sun is somewhere at the center, then the orbit is kind of squashed the way we can be able to see it at this point. Now, since the force that keep object to move around the earth is called the gravitational force, this force is not going to be constant throughout, because the radius, you can see the radius or the distance of the object and the sun is varying. This distance, when it's here, the distance will be different. When it's be at this point, the distance is also going to be different. So for that reason, the force of attraction is going to vary as the object move around. When the object A, now we are talking of this object A, when it's at point A, this object, when it's at the point A, it experiences a strong gravitational force. Yeah. So here it will be having a very high speed, meaning the kinetic energy at this point will be very high. But as it's moving in this point, kinetic energy will be converted to gravitational potential energy. So the speed of the object will be decreasing as it's approaching B. When the object has B, it has maximum, here it has maximum GPE. At this point, it has maximum kinetic energy. So meaning when this object is moving from A to B, kinetic energy will be converted to potential energy. So the object will be slowing down. And then when it's moving from B to A, the potential energy will be converted to kinetic energy. So kinetic energy will be increasing, then it means the speed of the object will be increasing. So if you are asked to state and explain the transfer of energy transfer that takes place as the object moves from A to B, you need to say that kinetic energy stored decreases while gravitational potential energy increases at that point. And the explanation will be according to the law of conservation of energy. Energy cannot be created nor destroyed, but it can be converted from one form to another. We have Jupiter, and Jupiter is 7.8 times 10 to the power 11 meters from the sun. The speed of light in a vacuum is 3.0 times 10 to the power 8 meters per second. You are asked to calculate the time it takes the light to move from the sun to reach Jupiter. I already have told you that time is distance over speed, but you have to check the distance given. Is it in meters? Yes, very good. We are happy with that. That the distance given here is in meters. So meaning we can be able to use it the way it is, and we shall have 2,600 seconds as the time it will take the light to move from the sun to Jupiter. But if you are given distance in kilometers, my prof learners, remember you have to convert that distance so that to meters, so that you can be able to fit the speed, which is in meter per second. So those are kind of the areas that you have to be very careful with. Our galaxy, remember the universe is made of billions and billions of galaxies. The galaxy that contains the sun is called the Milky Way. And when you were learning about cosmology, which is the study of the origin of the universe, according to the Igcse specification Cambridge, you are supposed to learn using Big Bang theory, because I understand we come from different backgrounds and different races. We have different beliefs regarding the origin of the universe, but the one that supports the universe observation support is the Big Bang theory. And Big Bang theory claims that the universe began and from a single dense point. It claims that the universe originated from a single dense point, and this hot dense point actually expanded over time to become the universe. Yeah, that the universe originated from a single dense point that expanded to become the universe. And there are different evidence that try to justify this. One of them is the redshift that is observed from the light that is emitted from the galaxies, which indicate that the universe is expanding up to this time. Also, the cosmic background microwave radiations, which are present everywhere and spreading in all direction, is an indication that if they are spreading in all direction and they are everywhere, it means that they were created from during Big Bang, shortly after Big Bang, and then now since they are spreading in all direction, it means that the universe has expanded and they were created from a single dense point. Now, state the theory of the universe that this observation support this Big Bang theory, and state when the radiation C, we are told that cosmic microwave background radiation is observed in all directions in space, and we have said they were created shortly after Big Bang. Explain why the radiation is now in a microwave region of electromagnetic spectrum. Now, since the creation of the universe, you are going to write in your exam that since the creation of the universe has expanded and the radiation has been shifted to the microwave region of the electromagnetic spectrum. I believe we are together up to that point. And if you are new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload another tutorial, you'll be notified. More will be coming, so consider subscribing. A galaxy is approximately 1.2 times 10 raised power 26 meters from the Earth. A scientist observes light from the distant galaxy. The wavelength of the observed light is longer than the wavelength of the light emitted from the galaxy. What is the name of this effect? This is redshift. When the wavelength becomes longer, it means it has shifted toward the red part of the spectrum. But if the wavelength became shorter, we could have talked about a blue shift, shifting toward the blue side of the spectrum, because the blue section of the spectrum has waves of shorter wavelength, and the red section of the spectrum has waves with longer wavelength. So when we are observing that the wavelength has becomes longer, then we say it's a red shift. It has moved toward the red part of the spectrum. Now we are supposed to state the name of Hubble's constant. State the current estimate. Oh, sorry. State the current estimate for the Hubble's constant. Current estimate is around 2.2 times 10 to the power negative 18 per second. This is the unit for Hubble's constant. Calculate the speed at which the galaxy is moving away. According to Hubble's law, Hubble's constant is equal to the speed of the galaxy divided by the distance the galaxy is from Earth. So if we can make V the subject of the formula, we can say now speed of the galaxy is equal to Hubble's constant times the distance from the Earth. And the distance of the galaxy was given here, 1.2 times 10 to the power 26. Then we are going to take Hubble's constant that we have written, 2.2. You should know this. 2.2 times 10 to the power negative 18 times the value that we are given here, and that becomes 2.64 times 10 to the power 8 meters per second. These are the speed at which the galaxy is moving away from the Earth. Scientists have measured the speed at which the distant galaxies are moving away from the Earth and their distances from the Earth. This measurement suggests that the universe was once a single point. Explain why. And in the process of me moving around and beating around the words, I came to a conclusion that for us to respond to this question, we're going to say the fact that the galaxies are moving away from the Earth, it suggests that the universe is expanding and the galaxy were closer together. Since they are moving away from the Earth, it means at one point they were closer together. This implies that at one point, galaxy and matter and all matter in the universe were once concentrated at a single point. So if you write that in your, ensure you capture that information in your answer, then you'll be able to earn the 2 marks that were provided. So the key points, the key areas that you are to mention that ensure that since the galaxies are moving away from the Earth, it indicates that the universe is expanding and matter was at a single point. So ensure that you have these 2 points in your answer. Calculate the average orbital speed. Orbital speed is given by the formula 2 pi r over t, and t is the time it takes to go around the orbit. The time it takes to go around the orbit is the one that we call t. But if we are working out the orbital speed in kilometer per second, so something that you need to realize is that r was given in kilometers, and we are also told that the Mars orbits the Sun in 390 days. Then we have to ensure that our time is in seconds. So it would be 690 times 24 times 3600, because in 1 hour we have 3600 seconds. So working it out, we are going to get our answer as 24 kilometer per second. The shape of orbit of planets is elliptical. The shape of the moon is circular, and the shape of a comet is quite elliptical. It's more elliptical. So let's talk of a planet. So if we have a planet like this, the shape of a moon is circular. If we are talking of the sun, the shape of a comet is elongated. Explain what's meant by redshift. Redshift means uh, the wavelength of light emitted from the distant galaxy increases. This occurs when the galaxies are moving away from the Earth. So meaning that the wavelength becomes longer. It means now the if you are told to explain what's meant by redshift, you're going to say that redshift means that the wavelength of the light emitted from distant galaxy increases, and this only occurs when the galaxies are moving away from Earth. If the galaxies were moving towards the Earth, it means the wavelength will decrease, and that is a blue shift. But when wavelength is of light emitted, where but when the wavelength of the light observed increases compared to the light emitted, then in question number 3, we are supposed to explain what's meant by redshift, and we are going to say that redshift means that wavelength of light emitted from distant galaxy increases when it's observed. This occurs when the galaxy moving away from the Earth. We are supposed to state the quantity that the redshift of galaxies used to calculate. This is actually used to calculate the velocity at which the galaxy is moving away. Once we know the wavelength, the change in wavelength, we'll understand at which velocity is that galaxy moving away from the Earth. Describe how the speed of Pluto varies as it moves from X to Y. That's what I've mentioned from the other section as it's moving from X to Y. Remember, at X, we are having high kinetic energy, and at Y, we have high potential energy, meaning that kinetic energy will be converted to potential energy, which implies that as it's moving from X to Y, kinetic energy will be decreasing, so which will mean the speed of this object will be decreasing. But as moving from Y to X here, the kinetic energy will be increasing, so the speed of the object also will be increasing at that point. Explain in terms of energy transfer why the speed of Pluto varies in this way. I've already mentioned what you are supposed to state, and also you can take this point now to write your answer down in your book. The average temperature of the surface of Pluto is 43 Kelvin. Now, if you are supposed to convert to degrees Celsius, you are going to subtract 273. Yeah, and we have a bright white surface and we have dark surfaces. Remember, from thermophysics, we learned that black surfaces are good absorbers of heat. They can absorb heat quite easily, but white surfaces are good reflectors of heat. So if the sun was on this side, or the sun is facing, if the Pluto is facing the sun, the white surface is facing the sun, the temperature of the white surface will take time to rise, because white surfaces are good reflectors of heat. They are poor absorbers. So the question is, explain how this affects this white surface affect the temperature of Pluto as it rotates on its own axis. Remember, the white surface I've mentioned is a poor absorber and a poor emitter. So when it's facing the sun, temperature will take time to increase, but when now it's facing on the other side, temperature will take a longer time to decrease, because white surfaces don't lose heat easily. Yeah. You need also to, already we have mentioned the equation you can be able to use to work out orbital speed, and r we said is the average radius of the orbit. Time is t is the time it takes the object to go around the orbit. Suggest why countries that are significantly distant from the equator experience significant temperature variation throughout the year. And remember, the temperature is depends on which part is facing the sun. So rays from the sun strikes the country for different number of hours per day throughout the year. Yeah, and also this country will be facing the earth at different angles, so that will also affect. You need to understand the stages and evolution of stars when you are going to sit for your exams. So we are supposed to fill in these gaps. The stage that follows the stable star life cycle of a star is called what? A red super giant. Why are we saying red super giant, not red giant? Is because it was massive star. So it will move to a red supergiant. It will then explode as a supernova to form nebulae, which will create other stars. But what will be left out is a neutron star or a black hole. Yeah. A galaxy is moving away from Earth with a speed of 33,000 kilometers per second. The value of Hubble's constant is 2.2 times 10 raised power negative 18 per second. Now, we are supposed to calculate the distance. Then, in order to work out that, we are going to use Hubble's law, right? Which is the speed of a galaxy is equal to Hubble's constant times distance. Then, for us to work out distance, we are going to rearrange this formula, and it will be now speed of the galaxy, speed of the galaxy over Hubble's constant. But something that you need to understand is that we were given the speed in kilometer per second. So I had to multiply 10 power 3 so that I can convert this speed to meters per second. So times 1,000 on this so that you can convert this kilometer to seconds. At the same time, we are asked to give our answer in light years. So down here, I also converted 1 light year is equivalent to which distance, right? So 1 light year is equivalent to a distance traveled by light in 1 year. 1 light year is equal to distance traveled by light in 1 year. And you remember distance is speed times time, and the speed of light is 3.0 times 10 to the power 8 times time. Time must be in what? In seconds. But in a year we have 365 days times 24 hours times 3600. We have our distance that is traveled in 1 year to be 9.4608 times 10 raised to the power 15 meters. So you'll now have to put it here, because if you just use 33,000 times 10 to the power 3 divided by 2.2 times 10 raised to the power 18, you'll get the distance in meters. Then you have to divide by distance traveled in 1 year, so that's going to be equivalent to that. In question number 9, we are told the figure shows the Sun as the central dot and the planets Saturn, Jupiter, and Earth labeled S, J, O, and EO. The planets orbit the Sun anticlockwise from the Earth's orbit, and the planets appear aligned as shown here. That's quite interesting. It's a good question. It's a good question. Then we are told that I can see. Let me just move down here. We're told that assume this, that Saturn takes 30 years to orbit the Sun and Jupiter takes 12 years. So, which means that the Earth just take 1 year, because if the Earth is taking 1 year, after 5 years it will be making 5 revolution. After 12 years it will make 5 revolution, like that. Now the question is, mark the position of Saturn and Jupiter 5 years after the original position. 5 years. So if Jupiter take 12 years to orbit round, it means after 5 years it will be somewhere here. Yeah, it will be somewhere here. And how do you get that? How do you get that? How do you get that? After 5 years, it will be at this point. And for Saturn, after 5 years, Jupiter will be somewhere here. And after 5 years, Saturn will be somewhere here. After 5 years, Saturn will be somewhere here. Now, how did I come to a conclusion that Saturn S1 will be here and Jupiter J1 will be at this point? Now, we were told that Saturn takes 30 years to orbit. Yeah, Saturn takes 30 years. So remember, it means that 30 years is equals to 360 degrees, because if it's taking 30 years to go round, it has covered 360 degrees. So the question you will ask yourself, 5 years, how many degrees will it have moved? It will be 5 over 30 times 360, and that will be 60 degrees. So meaning that you were to bring a protractor and then place it here, you measure 60 degrees in that direction. That will be its position. Then let's move to Jupiter. Jupiter takes 12 years to orbit. So meaning for Jupiter, 12 years is equals to 360 degrees. It has made one revolution. What about 5 years? So it will be 5 over 12 times 360, and that will be 150 degrees. That will be 150 degrees. So you are going to take your protractor and then measure 150 degrees from the original position. So meaning that you are going to place your protractor like this. I'm trying to show you what you are going to draw. You are going to put your protractor like that, and then your protractor will be this way. So you are going to, this 90 degrees. You are going to measure your angle in this direction like that, like that, like that. So the new position of J1 will be here, because to be you'll measure 150 degrees in the anti-clockwise direction. The next part also, you are told, mark the positions of Saturn and Jupiter 20 years later. So for Saturn, it's going to be 20 years over 30 times 360, because the period for Saturn was actually 30 years. So if you work it out, you are going to get 240 degrees. 240 degrees. So 240 degrees, 240 degrees, where will it be? We are going to measure up to this point, we have 180. Up to this point, in this direction, we shall have having 180 degrees. Then to get to 240, we need to add 180. How many degrees do we need to add? 60 degrees. So if you add 60 degrees, you'll have the fact that Saturn will be in this position. So in this position, this will be Saturn. So Saturn must have moved how many degrees now? Must have moved 240 degrees. But for Jupiter, Jupiter 20 years, it means how many revolutions has it made? Because it will be 12, 20 divided by 12 times 360. How many degrees will it make? Which will be 20 divided by 12 times 360. That will be 600 degrees. So it has made those revolutions. And anyway, like how many revolutions will it make? Yeah, how many revolutions will it make? So let me just show you here. 20 over 12. Yeah, 20 over 12 because one revolution take for Jupiter, one revolution is equivalent to what? For Jupiter, one revolution is equal to what? One revolution is 12 years, right? So in 12 years, it has made one revolution, so it will be at the same point. Let me just take you back here. For Jupiter, yeah, let me just erase everything that we are having here. Yes. Now, if we are talking about for Jupiter, in 20 years, in 20 years, remember, one revolution for Jupiter is 12 years. So meaning, in one revolution, Jupiter will go round and it will be at the same point after 12 years. So how many years are remaining now? Is 8 years. So again now in these 8 years remaining, how many degrees will it cover for it to move from this point? Again, it will be 8 over 12 times 100. 8 over 12 times 360, because to be having 8 more years. So after the first 12 years, it will go round, it will be here. The remaining 8 years, it will continue going. So in that, we are going to say it will be 8 divided by 12 times 360, which will mean it also have moved 240 degrees. So it will move from this point and it will cover 240 degrees. Then you can see now it will be the same angle as this one. So they will be, both of them, they will be aligned, right? In 20 years, Saturn will be in this position, that is 240 degrees. But in 20 years, Jupiter will have gone one full revolution, and then in the 8 years, it will go 240 degrees. I believe you've understood why I got 240 here for Jupiter, and I got 240 here for Saturn. Right. So the next part, state what observation, what state what is observed from the Earth's orbit after 20 years. It will be observed that both Saturn and Jupiter are aligned. They are in the same straight line. They are in a straight line. They will be aligned from Earth. You will see that they are aligned. You can see they are in a line. Huh? Yes, you can see they are in a line. So which means that it will also be observed that Jupiter is in front of Saturn. When a person or an astronomer is observing here using a microscope, a telescope, using a telescope, he will observe that uh, he will observe that Jupiter is in front of Saturn. Yeah, the observation will be they are aligned, or Jupiter is in front of Saturn. Yeah, basically that's what you are supposed to do in that question. Let's move to the next area, get to see what was asked. Choose two words from the list to describe each planet. Jupiter is a large and gaseous planet. Jupiter is a large and gaseous planet, and we can also say Earth is small and rocky. And if it's large and gaseous, it's going to have a low density because it's composed of gases and has a large volume. Earth has a high density because it's a solid and it's small. It's solid and small. Gravitational field strength of Jupiter is going to be large, so it has a large mass, and Earth has a small mass, so it's going to have a small gravitational force. Moving to D, here we are supposed to work out the mass of Jupiter. We shall use the formula density equals to mass of volume, but we need to rearrange the formula so that we can be able to work out mass, and mass will be density times volume, which means that our density has to be in density is okay because we are working out the mass. Density is much fine, 1300 kilogram per meter cubic, but the volume is not in the good unit. It's not okay. It's not okay. We have to convert this to meter cubic. So we are going to take kilometer. We write 10 power 3 because 1 meter is equal to 1,000 meters. So which is 10 power 3. Now since kilometer is cubed, so we are going to cube that. So the process I'm doing here is to convert this volume to meter cubic so that I can be able to use it. All right. So if I work it out, I'm going to get my mass to be 1.82 times 10 raised power 27 kilogram. And by transferring this answer here, you are going to make the examiner happy, and you're going to get your 3 whooping marks. 3 whooping marks. So that 1 light year is equal to 9.5 times 10 raised power 15 meters. We said one light year is the distance light traveling in 1 year, which means that speed times time will give us that distance. And remember that time should be in what? In seconds. And that's what I did exactly at this point. If I you work it out, you are going to get 9.4608 times 10 raised power 5 meters. And if you round it correct to 2 significant figures, we are going to get 9.5 times 10 raised power 15 meters. Okay. State one measurement that is taken when determining the speed at which a galaxy is moving away. That's the change in wavelength. And this change in wavelength is going to enable us to work out the speed, right? Now, write down the equation relating V, distance of a galaxy, V and the distance of the galaxy. That's basically Hubble's law, which is Hubble's constant is equal to V over D. So this is the formula they wanted you to write. State how the distance, D of a galaxy or a far galaxy can be determined other than using the equation that we have given here. Now, the answer to this, of course, is using brightness of type 1 supernova. So, or you can even say using brightness, just you can write brightness of a supernova. Supernova. Yeah, brightness of a supernova can be used. Now, let me just tell you how that happens. A supernova is a very bright star, which is also known as an exploding star. In a galaxy, we have billions and billions of stars. But when a supernova explodes, it becomes so bright. So it's evident that astronomers use the brightness of stars so that they can be able to determine how far that galaxy is, because the luminosity of supernova is predictable. The luminosity, the brightness of a supernova is predictable, it's known. Then if they want to know the distance, how far the galaxy is, because a supernova is inside a galaxy, then they are going to use the formula apparent brightness, which is measured. They can measure apparent brightness. So apparent brightness is equals to luminosity is equals to luminosity over d squared, where d squared is the distance where the galaxy is from Earth. So which means that since luminosity of a supernova is known and apparent brightness can be measured, if the astronomers are able to measure the apparent brightness and they know the luminosity, they can be able to determine the distance of that galaxy. Yes, at Igcse level, you are not supposed to know whatever I'm telling you here. What you are supposed to know is that another alternative of knowing the distance of a galaxy, for instead of using Hubble's law, you can be able to use the brightness of a supernova. But whatever I've mentioned here is just to make you understand how it's done, because astronomers can be able to measure the apparent brightness and the luminosity of a supernova is known. Then they can be able to use this formula in order to work out that. I believe we are together up to that point. So let me just the next question here, we are told that stable stars transfer energy into space by emitting electromagnetic radiation from their surface. Describe what happens in the core of a stable star to release energy. Remember, in the core of a stable star, there is fusion of hydrogen and hydrogen nuclei, which forms helium. And in the process, enormous amount of energy is produced and then released into space. Right? Describe how the observed light differ from when it was emitted. We are told that on Earth, light from a distant galaxy is observed and analyzed by astronomers. This information is used to determine the speed at which the galaxy is moving away. So, to describe how the light is observed is differ from the light that is emitted, remember the light emitted uh, will be having a different wavelength compared to the observed light. So the observed light will have a longer wavelength than the emitted light, and this is because the wavelength is shifted towards the red end of the spectrum. Actually, this is the Doppler effect taking place here, because there is relative motion between the observer and the source. Then the wavelength that will be detected on Earth will be different to that was emitted on that distant galaxy. So since the galaxy is moving away, the wavelength that we are going to detect on Earth will be longer than that one that was emitted, and that's what we call redshift. State the quantity that astronomers use to determine the speed at which the galaxy is moving away. This is actually the change of wavelength, and this is also the alternative you can write. Hubble's constant h naught is equal to 2.2 times 10 to the power 18 per second. Calculate the distance from Earth. Remember, you can be able to use the speed at which the galaxy is moving and Hubble's constant to know how far the galaxy is. You can rearrange this formula and this becomes the main formula you are going to use. And substituting, you have to check the units that are here and the units that we have. So they are okay, then you can be able to substitute the formula 0.9 times 10 to the power 24. 5.9 times 10 to the power 24 meters. That's this question whereby we are supposed to estimate the age of the universe. For you to estimate the age of the universe, you are supposed to use t equals to 1 over Hubble's constant. So if you work it out, you are going to get your answer being 4.54 times 10 to the power 17 seconds. You have to convert these seconds to years by dividing by what? Because in 1 year, how many seconds do we have? We have 365 days times 24, which is in 1 day we have 24 hours, then times 3600. So if you take that value and try to put in the calculator, let's see the answer we're going to get, which is going to be 4.54 times 10 raised to power 17 divide by the answer that is 365 times 24 times 3600. If I work it out, you're going to get 1.4 times 10 raised to power 10 years, right? And the reason as to why we're getting this formula, this is the formula you should be using for estimating the age of the universe. Time equals to 1 over h naught, which is a Hubble's constant. And when you work it out, you are going to get your answer in seconds. So if they're asking years, you have to do something extra in order to get your answer. But where did you get this formula from? If you assume that the Earth is expanding at a constant rate, the speed at which the galaxies are moving away or the universe is expanding is V equals to D over T, right? And this is the distance of the galaxy, isn't it? Right? Now, or the distance where the galaxy will be at a given time T. So we can be able to rearrange this formula and have D equals to velocity of the galaxy times the time, right? So using Hubble's law, you can say Hubble's constant is equal to the speed with all the velocity over the distance. But D from this point is Vt, and then you can be able to see V and the V will cancel out. Then you will have your answer remaining as what? Hubble's constant equals to 1 over T. So we can say Hubble's constant is equals to 1 over T. This formula can be rearranged to T is equals to 1 over Hubble's constant. That's the formula we have here. But during your exam, you don't have to show all this, whatever I've written here. You should begin from this point. T is equals to what? 1 over Hubble's constant. 1 over Hubble's constant. Once you've done that, you'll earn all your marks. In question number 9, yeah, as a question recent here, we are supposed to identify the planets. You need to understand the order of planets, and this X is actually Venus. Describe the relationship that the table shows between the mass of the planet and the gravitational field strength. But remember, the larger the mass, the larger the gravitational field strength, and that is basically what it's showing. Explain why distance from the sun in table 9.1 is average value. So we know that the orbit of planets is elliptical, is not a perfect circle. So meaning the distances the planet is from the sun would be varying around the orbit. So that's why we had to say that. We have already done question to do with average orbital speed. Also take note of how to work out that kind of question. How are stars formed? Stars are formed when gas and dust particles called nebulae are drawn together by the gravitational force. So a protostar or protostars are formed from stellar nebulae. Protostar becomes stable when the inward gravitational force is balanced by outward force caused by the high temperature and pressure in the core of the star. The initial fuel that is used to power a nuclear reaction in a star is hydrogen, and then stars that are approximately the same size as the sun become red giants, which then form planetary nebulae with white dwarf at its center. We have come in question number 10. We are supposed to state what is represented in space physics by the symbol h naught, that is Hubble's constant, and the law or the formula that connects Hubble's constant velocity and distance is given here. The numerical value is this, but what is the unit? The unit is per second. Per second. Use the value of h naught to determine the estimate of the age of the universe. I've told from the previous section, you don't have to show anything. You just write this formula and then apply it here. In seconds, that's what you are going to get as the age of the universe. We are supposed to state here when the cosmic microwave background radiations were formed, and they were formed or created shortly after the formation of the universe, and they spread in all directions, so they are detected in all direction. I believe we've gone through all the areas that have been tested in recent years, and it's my belief that questions will be centered around these areas that we have worked. If you got value from Profland YouTube channel, consider subscribing so that anytime I'm going to upload a tutorial, you'll be notified. See you in the next video.